So LY, as I will call it, is an inhibitor that is in clinical development to inhibit RAF-B in various solid tumor settings. And what we have, or how we got there, is through it's from a totally different direction. Our interest in this context is chronic myeloid leukemia that has acquired more than one mutation in the driving kinase BCR-ABL, and we call those mutations compound mutations. Now, compound mutations that involve the T315 residue tend to be completely resistant to all other single tyrosine kinase inhibitors. However, if you combine Ponatinib with an allosteric inhibitor called Asciminib, you can actually restore sensitivity, and in a way you can hope that you can restore sensitivity also in a clinical setting. The problem is that Ponatinib is relatively toxic, and the concentrations required to see these results in vitro or in mouse models are too high, probably too high for a clinical patient setting. So we were trying to identify molecules that could replace Ponatinib in this setting, so successfully combining with Asciminib to restore inhibition of the BCR-ABL tyrosine kinase. And using an approach that I think is quite innovative is called really quantum biophysics, to model drug binding in a different way than compared to conventional computational modeling. We identified several compounds that would fulfill this paradigm. So in combination with Asciminib, they would restore kinase inhibition. And one of these molecules is LY. And so what we show in this abstract is that the combination of LY and Asciminib is actually effective in restoring kinase inhibition. And so we hope that this will lend itself to a clinical trial at some point in the future, and may actually also tell us a little bit about how this BCR-ABL kinase is regulated and how two drugs combine to inhibit the kinase.